Okay, so welcome to the session on visual design, sketching, and labeling. I'm Jonathan Roberts. I'm going to be chairing this session. We have 6 presentations here, and it's going to be an interesting session. If you have any questions, then please put those questions on a Slido, and we'll get to those in due course after the presentations. Follow up questions and other things on Discord. As usual, you know the rules, you know what's going on. Let's get straight to our first presentation, which is going to be Discursive Patinas, Authoring Discussions and Data Visualizations. And this is going to be by Tobias. Take it away, Tobias.
Now you should be able to hear me well. And you can see my screen, right? Yes. Cool. Hi, everybody. My name is Tobias, and on behalf of my co-authors Derya, Akbaba, Marian, Dörk, and Benjamin Bach, I want to present the paper Discursive Patinas, in which we explore how we can anchor discussions in data visualizations. To start things off with a little exercise, I wanted to show a visualization of homicide rates in the US and Canada. If you're willing to, given the tragedy and the severity of this topic, I want you to explore the discussion around this map. What do people say about this visualization? How do they react to the data? And this was the point in the presentation where I wanted to play cricket chirping noises, because as you can see nothing, because visualizations are just not equipped to display audience reactions. Yet there is so much people could say about this data. They could share personal stories to serve as testimonies from highly affected areas. They could provide background information that helps others understand the context of this data. They could provide suggestions on how to improve the color scale that is hard to read for vision-impaired people. Or they could just point out sampling bias that leads to problematic visual encoding up there. And overall, audience reactions can provide a plurality of narratives that help frame this visualization beyond framings the original author was aware of or had in mind. So the status quo of most visualizations is that they usually do not provide a back channel for audience reactions. Information flows from the visualization to the audience, not back. In some instances, for example, on social media or Reddit, people can comment on the visualization as a whole for everybody to see. But these comments are usually displayed separately, and there is no way for the audience to point out what part of the visualization they are talking about. So what we are looking for today is a way to give the audience a voice inside the visualization, allowing them to become part of it. And as it usually goes, we are by far not the first people to do this. There has been a lot of great work, mostly on social analysis, for example, by Jeffrey Here, Wesley Willett, or Hai-Han Lin, that uses different ideas to integrate comments into visualizations, for example, freehand drawings or map markers. And I'm talking about map markers because everybody knows what a map marker is, but this is not limited to maps. This basically goes for any visualization. But the problem of these map markers that we see in the US is that they are just not very precise. Do they refer to the exact spot they are on or to a wider area? And if so, how wide exactly? Up in Canada, we have some freehand drawings, and they can be very precise because you can very uniquely draw them. But if hundreds of people use them, they become illegible. So what we find is that it's hard to simultaneously have comments that are precisely scoped and able to scale. So how can we integrate discussions with scope at scale? And our answer is very much inspired by human traces on physical objects. And here we see how single touches of a human accumulate and lead to a patina that shows where and how people interacted with an object. And inspired by this, we provide a very simple solution, and we allow people to simply draw rectangles on the visualization, and with that make a trace and connect that to a comment with an optional category. We call this an anchored comment, and it's a starting point for a discussion as others can like it or reply to it. Single anchors are translucent. So the interesting bit here is when lots of comments occur in one area, this area actually becomes more salient. And we call this the discursive patina, as it shows where the visualization has been discussed more heavily. We built a system around this idea to allow people to easily create anchored comments and explore different patinas, and we deployed the system in the wild. And the other thing that is interesting about these patinas is that we can use their visual appearance to encode other information about the discourse on them. For example, what categories are frequently used, what comments draw many responses, and how different areas relate to each other in the visualization. We evaluate our prototype with a host of user studies that are too lengthy to explain in this talk. Please refer to the paper to get more details on them. And I will just skip to our results because they show that anchoring changes how comments are written and read. A basic example for this is that anchored comments are generally shorter because people do not need to refer to a specific area in writing. Anchored comments, and this is the more complicated thing, is they highlighted details, insights, and context in the visualization, and with that, they guide visualization interpretation. And similar work has been done before, again, in the realm of social analysis. But the interesting bit about our results is that this all happens very localized. Anchors invite for close readings of small portions of the visualization and allow to dig deeper and scrutinize what people think about the data and its visual encoding. On the other hand, when we zoom out, discursive patinas help navigate the discourse. In this example of the category encoding, we show how people criticized the color scale of the visualization, and it shows up in a bright red color on the bottom left. Similar to physical patinas, this emergent meta-visualization shows where and how the visualization has been touched and discussed by the audience. Yet, our studies also clearly indicate that patinas can overwhelm and obstruct people from properly reading the underlying visualization. I will get to why this problem may actually be an opportunity in just a second. First, I want to zoom out and talk about the relevance of this work. There is, I think, an interesting tension between visualization designers and visualization audience, on the other hand. Especially in settings like data journalism or data-driven storytelling, visualization designers cater to the audience by narrating digestible stories. As Nicole Hengesbach describes, they strive towards seamlessness to present visualizations that are easy to consume. And this is a good thing. I like easily digestible visualizations. On the other hand, as we have observed in discursive visualization, the audience narrates many potentially contradicting stories. They scrutinize the data, potentially making it more complicated. They reintroduce the mess designers have tried to keep out. And even if this mess can be overwhelming, it points towards a shift in the relation between visualization designers and their audiences, giving people the ability to change the visual appearance of a visualization and provide alternative framings. And this also is a very good thing. So let me tell you what you can do to discursify your own visualizations. And here I really just want to cherry pick some learnings that we made the hard way in our user studies. I do not recommend to build an annotation platform in the middle of nowhere on the internet and expect people to flock to it just because it's technically interesting. Because once we tapped into existing discourse and invited groups to annotate visualizations they are already thinking about and discussing, we got way more interesting results. Because what basically happened is that people just furthered ongoing discussions on our platform. I also want to highlight the importance of the role of the facilitator. Initially, we were very, very afraid to influence people by actively engaging in the discussion throughout the user studies. And we found that facilitating and moderating may set social norms, but it also encourages people to share reactions and stories in this, for them, yet unknown format. And finally, our idea was to set up a system that would work with just any visualization that we could find on the internet. And we did a lot of existing visualizations from Reddit. We included them into our systems. And we basically wanted to cater to as many people as possible. And we imagine how in the future visualizations are designed with audience discussions in mind. And for that, they need to concede space and visual variables to accommodate these discussions without obstructing the underlying visualizations. And with that, I thank you. I look forward to your questions. You can try the prototype with some demo visualizations and some visualizations from our user studies at viscussion.de. And thanks again also to my co-authors, without whom this work wouldn't have been possible. Cool. Thank you.
Many thanks, Tobias. So we have a question. Anna Offenbanger writes, what real world context could you imagine this being deployed within?
I really found it interesting, the idea to deploy this in a journalistic setting, because this already is a setting where the audience plays, like, people cater to that audience, and there is no back channel. I mean, we all know, like, the comment section of YouTube, which is a mess, and many formats have abolished this comment section because it's a mess. And I think with proper facilitation and moderation, and maybe also a more structured input from the audience, like an anchored annotation, I feel there would be really interesting use, not only in terms of storytelling and providing different narratives, but also as feedback to the authors of the original visualization. In the paper, we basically show 3 different scenarios of how we can see this applied in the real world, and yeah, I just recommend to check those out.
Cool. We have another question from Riley saying, could you extend this to non-static visualizations? Will this still work?
We really want to. We had this in the initial prototype, and there is just a combinatorial explosion that comes with this, because suddenly everything, like the state of every annotation, becomes view dependent and dependent on many variables. I think there is more work to be done here, because obviously, like, dynamic or like even filterable visualizations, this doesn't have to be complicated to not work all of a sudden. Would really benefit, and this would also basically also give rise to many more opportunities for this to be deployed in. Yeah.
Brilliant. Well, thanks very much, Tobias, for keeping on time and a great talk. We will
Thank
move
you.
on. Thank you. The next talk is active gaze labeling visualization for trust building, and this is going to be by Maurice Koch, and we're going to play a video, please. Thank you.
Hi, my name is Maurice Koch, and on behalf of my co-authors, I'm presenting our paper, Active Gaze Labeling, Visualization for Trust Building. Eye tracking is commonly used to analyze the viewing behavior of multiple participants. The goal is often to compare and group them according to their gaze behavior. Area of interest are often employed to provide semantic interpretation of gaze, which facilitates the analysis of eye tracking data. The problem of AOIs is that their manual annotation is often very tedious. Automatic detection of AOIs is also very challenging, especially in free-viewing scenarios like the one shown before. There are alternative approaches to annotate gaze data. For example, gaze thumbnails, which provide a link between gaze points and the actual stimulus. These thumbnail representations can serve as a basis for the annotation task. Another problem of annotating gaze data is uncertainty. Annotation can be ambiguous and subjective, in particular because often fixations are labeled and not individual gaze samples. On the right, you can see an illustration of this problem. We might have a fixation whose samples are all within the boundaries of one AOI, so this fixation is considered easy to label. But there might be other instances where unambiguous label assignment is not so straightforward. For example, a fixation could be partially inside one AOI or overlap with another. This is a source of ambiguity that is challenging to humans and automatic approaches alike. To address these challenges, we present an uncertainty-aware visualization for automatic annotation of gaze data. Our visual analytics approach consists of a 2D embedding of gaze thumbnails, which you can see here in the center. Additionally, we overlay a multi-class heat map on the 2D embedding. We also provide the user with 2 interactive lenses to explore the landscape of gaze thumbnails. Since our approach integrates active learning, we have access to classifier predictions which are visualized using iFlower glyphs. Last, the user has also access to comment training and filter options. In the following slides, I will provide further details about these individual components. As mentioned before, we provide users with 2 interactive lenses to explore the landscape of gaze thumbnails. This has also given me an opportunity to better explain the structure of the 2D embedding. For each fixation, its center sample is connected to all other of its samples via links. Again, all samples here refer to individual gaze thumbnails. However, we only expose those links when the user brushes over the area. Thus, the outgoing lens provides details on demand by revealing connections between the center fixation and related gaze samples when brushed over. The incoming lens serves a different purpose. It exposes all fixations with at least one sample being within the brushed area. This lens helps to detect annotation outliers, which can be helpful to maintain accuracy in the labeling process. Next, I want to discuss the multi-class heat maps. As mentioned before, we overlay multi-class heat maps on the 2D embedding. There is one heat map per label. A common problem in annotation is erroneous labels, which is here the red sample. We developed an overlap indicator that shows label outliers, effectively guiding the users to potential erroneous labels. iFlower glyphs show classifier confidence on a fixation basis. Each petal represents a label or class with the validate indicating confidence level. It also includes a gaze thumbnail corresponding fixation center. The entropy acts as an uncertainty measure of the prediction. Additionally, we show all fixation samples as small gaze thumbnails, which again helps verifying the classifier output. Now, as we outline the components of our VA approach, we want to focus more on the actual annotation workflow. The user starts creating an initial training set by identifying clusters in the 2D embedding. The interactive lenses facilitate this process and help identifying potential outliers. It's very common for users to produce erroneous labels. The retrospective analysis lets users review potential labeling errors guided by the overlap indicator and multi-class heat maps. In the active learning step, we train the first iteration of our classifier and perform prediction on unlabeled fixations. iFlowers help users to assess the classifier performance. Similar as after the initial labeling step, users can verify and correct potential erroneous labels in the retrospective analysis. We evaluated our approach with use cases on 2 different datasets. For the purpose of this presentation, I focus only on a single dataset. Our first use case is performed on a subset of Ego 4D, consisting of around 6,000 fixations. Our chosen subset contains a diverse set of entities, including food items, playing cards, and humans. With our approach, we could identify all categories and identify problematic categories such as cards and bricks with many problematic fixations. Using the iFlowers, we could detect classifier improvements from iteration 1 to 3, especially in the cards category with noticeable fewer false positives. We also presented our approach to visualization experts with experience in machine learning. One participant additionally considered themselves an eye-tracking expert. The tool demonstration was similarly structured as the use cases. We asked the expert to assess the individual components of our approach. In general, we got positive feedback on the multi-class heat map and the iFlower glyphs. However, one expert noticed that the interactive lenses, while useful, were sometimes hard to interpret. To conclude, we presented an active learning approach for the annotation of multiple AOIs, to reduce the manual annotation effort and improving labeling accuracy. We devised several visualization and interaction components to facilitate annotation process under uncertainty. We noticed several directions for improvement. For example, improving the scalability, in particular with respect to the number of AOIs or entities, and assessing the annotation quality and performance in a controlled user study. Thanks.
Many thanks, Maurice. I think, Maurice, you are on the line. We don't
Yes,
have any questions in slide. We don't have any questions in Slido, but I do have a question myself. Can you talk a little bit more about scalability? I think when you have a sort of larger zoom area, you might get more elements, and sort of talk to us a bit more about how it scales.
Yes, so that's actually a big concern also during like the development of this tool, is that if we have eye tracking data, we usually have a lot of samples, which are like, there can be a lot depending on the sampling rate of the eye track as well. So technically, the scatter plot can of course show all of them. But yeah, that's definitely one of the limitations in terms of scalability. I think the other big problem is the number of AOIs, the number of classes that we have. And that's definitely something that also kind of impairs the annotation effort, or it actually impacts the annotation effort as well.
And I'll have another question because there aren't any more questions there. But I wondered if talk about the petal itself. Is there a sort of situation where someone might not know what to do because each of the weightings are about the same, and sort of how do you sort of resolve that?
Yeah, that's actually a case where we have uncertain predictions produced by the classifier. And these are actually interesting cases where we want the user to like assess in which class it belongs to, because obviously the classifier is uncertain about that instance. So yeah, that's kind of the user decision.
So you rely on the user to actually make a choice there of what to do, maybe.
Exactly. So
okay. Brilliant. Oh, it's very interesting work. Well, thanks very much, Maurice, for your presentation. And we're going to move on now.
You're welcome.
So our next talk is going to be a survey on non-photorealistic rendering approaches for point cloud visualization. And it's going to be by Ollie. Ollie, over to you.
Thank you very much. So I want to present a more computer graphics heavy topic, so sorry for that. And as 9 minutes are not really enough to present a 20-page survey, I just want to give a short introduction to the general topic and the structure of our paper so that you can decide whether it might be interesting for you to read. So our paper is structured into 2 major parts. In the first half, we provide a lot of background information on point clouds, the different types and their characteristics, how they can be rendered, what are typical data structures used. And then we introduce non-photorealistic rendering in general and for point clouds specifically. So I think that this first section is really interesting for anyone who deals with point cloud data and with point cloud rendering specifically. In the second half, we then present our survey. First, we outline our methodology and scope, and then we assess, review, and compare the different approaches and provide future research directions. Okay, now let's talk about point clouds. Point clouds are a spatial data representation, representing data as a set of points in space, and they are used in a wide range of applications. You can see some examples here. For example, in the context of digitization efforts and cultural heritage preservation. Point clouds are also used for cosmology. In image B, you can see a point cloud from a particle simulation that helps understand cosmological processes better. Point clouds are used in the area of geoscience, for example, for assessing and maintaining infrastructure, urban infrastructure, or monitoring vegetation stands. So these are some examples, but there are many more. Now, how can we really define what a point cloud is? Turns out this is not as trivial as we thought in the beginning, because the term point cloud has been used across many different disciplines throughout the years and with sometimes slightly different meaning. And also the authors who use this term, of course, have implicit assumptions on what this term means, but they do not explicitly communicate these assumptions oftentimes, and also the assumptions are not necessarily valid across all domains where this type of data is being used. So, for example, one common assumption is that a point cloud denotes a set of surface samples obtained via laser scanning. And while this certainly is a type of point cloud, it's not the only one. So, for example, we found that the point clouds that have been used in statistical mechanics, hydrodynamics, astronomy, multivariate data visualization, particle systems for movie production, computer graphics, and remote sensing. So in order to capture all these different disciplines and their approaches to point cloud visualization, we chose to use a very broad definition of what a point cloud is, namely that it's a collection of points in space without guaranteed structure or order. Each point, of course, has a position, but it may exhibit additional attributes. Now onto non-photorealistic rendering. This research area emerged from the area of image stylization, image abstraction, and the concepts there were then also applied to 3D scenes. And Lavon et al. In a recent survey provide a very good characterization of what NPR is about, even though they speak about illustrative visualization, which is not exactly the same, but nevertheless, they say that it is characterized by abstraction and simplification, by emphasizing the important, relevant, and suppression of the context, thus leading to clearer, more expressive depiction and consequently more effective visualization. You can see some examples for illustrative visualization here in the images. And now these ideas of abstraction and simplification to improve communication of information have also been applied to point clouds. And the thing with point clouds is that if you render them directly, the resulting images can be quite hard to interpret. They're ambiguous, oftentimes visually cluttered due to the unstructuredness of the data. And here NPR can help communicating information more effectively. For example, by emphasizing important information, as you can see in the first image where individual tree instances are highlighted. NPR approaches can be used to reduce the overall visual complexity of an image and to improve scene understanding. For example, in the middle image, you can see a see-through effect to understand the internal structures of an object. And also NPR can be used to create just aesthetically pleasing and engaging images. Now, we reviewed the NPR approaches for point clouds from the last roughly 20 years. You can see an overview of the approaches on the right side. And this is a full page in our paper. I think it really provides a nice chronological and graphical overview of the different approaches. So the first thing we do is we assess each approach individually using 7 dimensions. And I want to motivate these dimensions using what we think of as the design process for an NPR approach for point clouds, depicted on the left side. And the 7 dimensions we use for assessment are more or less the choices you make in this design process. So first of all, you usually have some data, point cloud data, acquired with certain acquisition methods. And the point cloud type method NPR approach assumes already tells you something about the assumed point cloud characteristics. And then you have a visualization goal. You have a purpose of why you want to employ NPR in your visualization pipeline. So, for example, maybe you just want to enhance overall scene understanding. Maybe you want to communicate specific information, or maybe you want to create artistic images. And the data and your goal, they form your use case. And then you go and choose a number of NPR techniques to combine into an overall approach. And with the NPR techniques, we focus on mostly the visual result. So, for example, NPR techniques are transparency, hatching, stippling, feature line enhancement, and so on. Then your overall approach has to be implemented. And this implementation operates in an implementation space. So there are object space approaches, there are image space approaches, and also feature space approaches that work on high dimensional feature vectors. And you utilize a number of, or one usually, but sometimes multiple rendering approaches. So, for example, point primitive rasterization is very common. Then you have splatting, ray tracing, and so on. So these are the technical details, one could say, of the approach. And the combination of the techniques and their implementation imply certain constraints and requirements. So for example, whether you need pre-processing for your approach to work, and whether certain per point attributes, such as, for example, surface normals, are required. These constraints and requirements then influence the applicability of your approach to other use cases. So these are the 7 dimensions we use for characterizing each approach. And you can see here there are the domains as well. We describe them in detail in our paper. So what we do is we assess each approach individually, and we compile this very compact and comprehensive table that gives you an overview of all the approaches and their characteristics and helps in identifying trends. And also, if you have a specific use case, you can take a look at the table to find suitable rendering techniques. And we, of course, do not only assess each approach individually, but we also compare them and talk about common trends. And because of the time limitation, I can't go into detail here. I just want to tell you the things we discuss, and then you can read the discussion for yourself. So we speak, for example, about commonly used point cloud types and also commonly used evaluation point clouds. So this is an issue because, interestingly, there are a significant number of approaches that are evaluated on point clouds that are actually the vertices of meshes, which is not very representative for the large number of real-world point clouds we deal with today. So this is an issue. We discuss frequently employed NPR techniques and their different variants, namely stippling, hatching, and brushing, as more of techniques that try to mimic specific artistic styles, transparency, and feature line enhancement. Then we speak about how do certain point cloud characteristics, such as density, for example, influence the applicability of certain NPR approaches, what are typically used data structures, and how are level of detail approaches for massive point clouds incorporated. Now, if you're interested, I invite you to read our paper. Thank you for your attention, and if you have any questions, feel free to ask them now.
Many thanks, Ollie. That's really good. It's a good insight to have as an overview. So I think we have a question from Anna asking, what is available resources, sort of hardware processing power, as a sort of a factor considered in your table and classification?
Sorry, could you repeat this?
So was sort of hardware and computational processing a consideration of yours?
Yeah. Yes, we talk about that a little bit. So in our first half, we talk about hardware acceleration in general and how point cloud rendering historically was influenced by the advances in hardware acceleration and what are commonly used techniques there. Then something we noticed is that most of the approaches work on quite small point clouds or are evaluated on quite small point clouds that probably everyone can render with any machine or mobile phone or whatever. So this is really an issue because the point clouds we deal with today are not that small. They're massive, terabytes of data that have to be streamed sometimes. So this is really one of the points we suggest for future research directions, to look into how can the streaming of point clouds and the LOD approaches that are required, how can they be combined with non-photorealistic rendering? Because if you have LOD approach, this usually causes some kind of discontinuities. Chunks are maybe popping in and out that are streamed in real time. And if you have very unstable NPR approaches, this might have a heavy influence. So yeah, this is definitely something that should be looked into a little bit more. Of course, every author does in a runtime, or most of the authors does do a runtime evaluation of their approach. But as I said, mostly not with data that is representative, actually. Okay, yeah. So I mean, there was a question about challenges. I have a sort of a broader question which will lead into that. Is did you sort of notice any trends? It looked from one of your pictures that the earlier works tended to be more silhouette based, and the later works more sort of transparent. Yes.
And then sort of moving on now, what are the open challenges? Can you sort of say a bit more about sort of that trend and then towards the open challenges?
Yeah. Yeah, so what we found is that in the earlier years, the focus was more on mimicking specific art styles known from handmade illustrations, so hatching and stippling and so on. And nowadays it's more about actually transparency, yes, also neural stylization, so employing neural networks for example, style transfer, stuff like that. Also combining multiple different approaches, so approaches known from image stylization with point cloud rendering, for example. We have some techniques that were used throughout all the years. So for example, feature line enhancement was relevant in every year, I would say, because it's just so powerful in conveying shape and enhancing scene understanding. And yeah, so we see a shift there. And regarding the challenges, so I think there are many. I want to highlight maybe one, multi-temporal point clouds, because most of the approach, so actually all of the approaches work with static point clouds. And in the realm of particle visualization, we usually have multi-temporal point clouds and we have approaches there. But if we have surface point clouds from, for example, LiDAR scans, multi-temporal point clouds are not really considered yet, even though this data starts to exist because municipalities start to capture their infrastructure regularly. And here's the question, can we maybe adapt approaches from particle visualization to this domain, other cross-domain synergies that are yet to be explored? So this, I think, a really interesting question.
Okay, well, thanks very much, Ollie, for an interesting talk. And I think people need to look at the paper, I think, to understand all what was going on. So well done. Thanks very much for the talk. Okay, let's move on now. So the next talk is going to be interactive reweighting for mitigating label quality issues. And the speaker is going to be Weikai Yang. Over to you, Weikai.
So yeah, I'm gonna share my screen. So, hi everybody. I'm Weikai Yang from HKUST Guangzhou, and today I would like to introduce our work interactive reweighting for mitigating label quality issues. And in practice, it is usually hard and even impossible to manually address all data quality issues due to the large amount of training data. And one promising way is sample reweighting, which tries to reduce the negative effect of low-quality training samples. And the state-of-the-art methods use a few validation samples to decide whether the training samples are beneficial to the model. And specifically, it first calculates the model performance on validation samples. Then a higher weight is assigned to the samples that increase the performance, and a lower weight is assigned to the sample that decrease model performance. But in practice, there are still some low-quality validation samples which can cause the wrong reweighting results. For example, the jacket here in the validation sample is mislabeled as shirt, and you can see that there are some more training samples which are also jacket but mislabeled as shirt are now considered beneficial to the model and assign higher weights. So we need to efficiently identify these low-quality validation samples and then improve them. And there are several challenges in improving the validation samples. First, existing methods usually construct the validation samples based on some measures like the loss or the prediction confidence, which usually results in the noisy annotations and biased distribution in validation samples. And this will require experts to analyze the reweighting relationships and then correct them. In addition, the reweighting relationships are usually of large scale and users are not familiar with them. So we need to provide a user-friendly interface to help experts explore and analyze these complex reweighting relationships. So our solution consists of two parts: an automatic validation sample improvement method and a reweighting relationship visualization. So here is the system overview. At first, in the data preparation, we extract the reweighting relationships between validation samples and the training samples. And these relationships form the bipartite graph, which will be used to automatically improve the validation samples. And it then also performs co-clusterings and visualize both the clusters and the reweighting relationships so that to facilitate the exploration and analysis. Users can then make informed adjustments based on the analysis, such as adding some necessary validation samples, correct those noisy annotations, and adjust the sample weights. So we first introduce our automatic validation sample improvement method. Previous reweighting methods treat the validation sample as a whole, which makes it hard to identify those low-quality validation samples. So therefore, we first decompose the reweighting relationships to calculate the influence of each individual validation sample. And by doing so, we can find that the validation sample V2 here assigns negative weights to high-quality training samples S2 and S4, and while assign positive weights to low-quality training samples S3. So this is a very bad validation samples. And after identifying this, we can reduce the weight of V2 and obtain a better reweighting result. And so now the problem is, how can we measure the quality of validation samples and then remove those low quality ones? So here, we consider the correctness, which aims to generate the correct reweighting results, and the balanceness, which ensures the balanced weights across different classes. And since there are two optimization goals, we use the multitask learning to automatically adjust the weights of these two terms. And we conduct experiments to evaluate the proposed method. And the results shows the effectiveness of our automatic methods in both simulated and real-world datasets. And it can also well handle both noisy labels, the imbalanced class distributions, and their hybrid. Next, I will talk about the visualization part. So to help users analyze and further improve the reweighting results, it is necessary to visualize the reweighting relationships. However, there are massive complex reweighting relationships. So if you have 100 validation samples and 2,000 training samples, then you will get a million of reweighting relationships. And so to address this, we employ co-clustering. And it first will discretize the reweighting relationships into positive, neutral, and negative, and then perform the co-clustering to obtain the validation sample clusters and training sample clusters. These clusters are then visualized on the left side and the right side respectively, and the link in the middle is the aggregated reweighting relationships, so that it is much easier to explore. And users can efficiently explore the samples and make informed adjustments in this visualization. And we conducted 2 case studies to demonstrate the effectiveness of our developed systems. So in the closed dataset with real-world noisy labels, our system helped identify the mislabeled samples between similar classes, such as knitwear and sweater. And in the OCT dataset with both noisy labels and imbalanced class distributions, our system helps identify both the mislabeled samples and also the poor coverage in validation samples. And I will introduce a little more about the second case. So at first, the experts examined those low-weight validation samples, which means that they are not used after our automatic validation sample improvement. So after examining the image contents, the expert confirmed that they are mislabeled validation samples, and our methods has successfully identified this and removed their influences. And of course, experts can explore the corresponding training samples and to identify more mislabeled samples. And experts can also start analysis from training sample. And for example, he identified 4 samples that are considered high qualities but still receive negative weights. And by examining these samples and through the associated reweighting relationships and also the corresponding validation samples, they found that these symptoms are not covered by the validation samples, so that these samples are considered not beneficial to the model training. And to address these issues, the experts will consider adding more of validation samples that contain this symptom, so that the reweighting can work better. So in conclusions, we developed a visual analytic tools for improving the sample reweightings. And it contains the automatic validation sample improvement method and a biparty graph-based visualization to support interactive explorations and analysis. And of course, there are many interesting future work that deserve exploration. And for examples, currently we recommend samples that are likely to have long reweighting results for examination. And it would be more interesting if we can dynamically recommend the samples of interest based on users' previous adjustments. And the second one is about supporting the online monitoring so that users can check the model performance and the reweighting results across different epochs and make adjustments in time. And also, currently, our tool is evaluated with the image classification, and it would be more interesting if we can extend it to more tasks and to verify its effectiveness. And thank you all, and I'm happy to take any questions.
Brilliant. Thanks very much, Weikai. Just checking to see if we have any questions. I can't see any questions, but I do have one myself. Could you tell me or tell us a bit more about your feedback mechanism? So the expert in your example is saying that maybe some of those low weights or inconsistent training examples, how do they then go and change them? What is the interaction capability of your system? How is that actually happening?
Yeah, so for example, users can, if from the validated sample part, he can find that these samples are mislabeled and so that their weights should be further decreased. And also if they found that the model incorrectly reduce their weights and they can increase them so that users can manually adjust the weights. Another useful interactions for validation sample is that, like in these examples, they found that there are some missing or poor coverage in validation samples, so that the experts can decide to adding some samples, for example, these two CMV images to improve the coverage of validation samples. And for the training sample part, usually we don't require users to manually adjust them, but they can simply mark some as correct or incorrect, so that this will be fed into the reweighting mechanism to adjust how the reweighting mechanism will work.
So does your interface allow people to mark them up in a way, or to select them, or to drag them? Okay.
Yeah.
Brilliant. Well, thanks so much for a good talk and interesting work. Thanks very much. Let's move on to the next talk. The next speaker is going to be Jing Ku, who's going to be talking about graph transformer for label placement, and we have a video to play for this. So please play the video. Thank you.
Good morning, everyone. I'm Jing, and I'm here to present our research titled Graph Transformer for Label Placement. Thank you for the opportunity to share our findings with you today. I will introduce our work from 5 aspects. Short text annotations, typically referred to as labels, are a popular approach to interpreting crucial elements of a scene and have been extensively utilized in graphic design, information visualization, and AR/VR. The placement of labels greatly affects users' comprehension of the scene, from labeling point features such as cities on a geographical map, to placing labels for area features such as tissues in medical illustrations. There are many open problems in label placement due to its NP-hard nature. Manual label placement is a time-consuming process, which has led to ongoing research into automatic label placement for decades. According to label positioning, label placement tasks are generally categorized into 2 types: internal and external. Recently, a few studies have introduced learning techniques encouraged by the success of deep learning in various domains. However, the progress in addressing two critical challenges is still limited. First, traditional rule-driven solutions struggle to capture the complex interactions between labels. Second, training and evaluation data ideally require non-trivial effort and expertise in design, thus resulting in a lack of decent datasets for learning-based methods. In this work, we will address both challenges with novel contributions. First, we formulate the task with a graph representation, where nodes correspond to labels and edges to interactions between labels, and treat label placement as a node position prediction problem. With this novel representation, we design a label placement graph transformer, LPGT, to predict label positions. Second, to limit the shortage of high-quality benchmarks, we construct a new dataset. The illustration from commercial areas. Now we adopt external labels for graphics. The key components of an external label include text, label box, and anchor. Given a set of labels to be placed in a graphic, we define the label placement problem as follows. The input includes an image and raw label information. The anchor positions and box size form the label information. The output is expected label positions. Based on this problem definition, we design the architecture of LPGT. It contains two main stages, graph construction and displacement estimation. In the graph construction stage, a complete graph is constructed to capture the relationship between labels. Its node and edge features are generated from the label information and the image features. For each node, we concatenate the label anchor point and the box size as a geometric part of its features. To build the features of each edge, the distance between its two nodes is computed and concatenated with the size of two corresponding boxes as a geometric part of its features. To capture the image features for each node, we first extract deep features maps from the entire image by a CNN. Then we utilize a feature align strategy to avoid the misalignment between the node and its selected feature vector. We construct a patch centered on the node. The deep node features are generated by applying an average pooling over the patch features. For the deep features on an edge, we extract rich visual information from its bridge across the two nodes. We sample the pixel points along the edge and apply an average pooling over deep features of all points. Using the graph representing the labels, LPGT iteratively learns the displacements of nodes to construct the label layout. It consists of sequential GN modules with the same architecture but different widths, adapted to the multi-step estimation of the node displacements. Each GN module comprises three main components: encoder, transformer layers, and decoder. In the encoder, we design a feature fusion mechanism to jointly integrate label information and image features into the representation learning of nodes and edges. The core block consists of several transformer layers, and each transformer layer contains a node transformer layer and an edge transformer layer. The node transformer layer achieves the aggregation and updating of node representations based on the node level attention. It projects QKV vectors from each node representation, simultaneously conditioned on the edge representation between two nodes. We further propose an edge level attention conditioned on node representations to explore the interactions between label relationships. The edge level attention projects QKV vectors from each edge representation and associated node representations, then as the QKV vectors of edges and nodes. The decoder predicts the displacement of each node and the distance vector between any two nodes. To train LPGT, we design three losses: displacement loss, distance loss, and overlap loss. The displacement loss is designed to guide labels to the expected positions. The distance loss is proposed to optimize the spatial relations between any two labels. To reduce the overlap between labels, we design the overlap loss. To address the dataset issue, we built a new dataset named the Appliance Manual Illustration Labels dataset. Illustrations from household appliance manuals are typically created by professional designers. Thus, we manually extract useful label placement information from each illustration. The dataset contains 869 label layouts across 11 appliance categories. We evaluated the performance of LPGT by comparing it with 11 GNN models and 4 label placement methods on the proposed dataset. We also conducted a user study and ablation studies for more evaluation and analysis. The quantitative comparison demonstrates that LPGT is effective and robust for placing varying numbers of labels across different object categories. The predicted label layouts of several illustrations are visualized in the figure. LPGT achieves appropriate label layouts with less overlapping and clutter. The user study suggests that participants prefer LPGT-generated layouts over those from other methods, aligning with both the quantitative and qualitative results. Based on the findings that variations in the key designs of LPGT influence overall performance, the ablation studies indicate the effectiveness of this design. Finally, some limitations of our method need to be explained despite its promising performance on label placement. To reduce the computational complexity of edge-level attention, we restrict each edge to attend to its neighbor edges. Thank you for the opportunity to share my work with you today. I look forward to your feedback and questions.
Many thanks, Yukai. I think you're online. If you're there, I think your audio, you might be able to speak with us. I haven't seen any questions on Slido, but I do have a question if you are there. When label placements quite often happen, the algorithms look at different strategies, whether they're above or below or to the left or around the sort of the anchor that you're trying to put down. Do you sort of deal with this sort of position, or do you always have these external labels?
Oh, okay, I'm online. Oh.
Are you able to, did you hear my question? Are you okay to answer?
Yeah, I heard your question. Can you hear me, Chair?
Yes, I can hear you. That's fine.
Oh, okay. Yeah. In fact, in our method, we don't care the positions of labels refer to the illustration. We just leave this problem to the network we built. Yeah, it works automatically to place labels. So there is no matter with the specific positions of labels referring to the illustration. Yeah. Okay.
One of the other challenges typical with label placements or these visual placement of labels is quantity. So when you get lots and lots, you have to release some criteria, and quite often some of the algorithms actually delete labels. I mean, what happens with your algorithm when you get too many labels to place down?
Oh, okay. In fact, there are different numbers of labels in our samples. For example, someone has only 2 labels, someone has many labels, such as 20 labels or 30 labels. But we can solve all these cases. Yeah. But there is maybe some limitations because we don't try 100 or 200 labels. Maybe it's a good future work for us. Yeah.
Yeah, I mean that's a challenge, isn't it? When you've got too many labels and not enough space to put them down, it's an impossible challenge to solve. And you have to prioritize some of them.
Yeah.
Well done. Thank you very much for some very good work.
Yeah.
And we're going to move on to our final presentation now, which is Data Garden, formalizing personal sketches into structured visualization templates. And this is going to be given by Anna. Thanks so much. Over to you, Anna.
Hello. Is my audio all right?
Yeah, that's fine.
Awesome. Okay, great. So thank you for taking the time to attend this presentation. I'm Anna Offenwanger, and I will be presenting the work Data Garden, formalizing personal sketches into structured visualization templates on behalf of myself and my colleagues, Theophanis Sandilis and Fanny Chevalier. Here we go. Sketching is an effective means of communicating intent. Allow me to demonstrate. Let's say I want to make a visualization of my personal activity data. I want an organic plant-like type graph. And to clarify what I want, I can just sketch it out for you. I want branches that represent days, leaves that represent activities. I want the color of the leaves to represent the type of activity, and the position of the leaf to correspond to the time the activity took place. So in a very short amount of time, you now know what I want for my visualization. If I were to give you this graph that I've drawn, my explanation, and a set of data, you should now have everything that you need to create a final visualization. These components, specifically the sketch and the explanation, are what we call a sketch-based template. The process of creating the template and applying data to it to create a visualization is what we call a sketch-based templating workflow. This kind of workflow is actually quite common already. Visualization designers will use sketches to clarify their intent before creating a visualization. Sketching also has the advantage that it's approachable for a general audience. You can create very unique and personal visualizations through sketch-based interaction. However, it's difficult to iterate on these sketches, and manually drawing out map data is tedious. Existing visualization systems just don't support this kind of workflow. Therefore, we built Data Garden to demonstrate how a system could support a sketch-based templating workflow. I will now run through a quick example of specifying a template in Data Garden. So you start the same way as you would in a normal sketch drawing your visualization. You'll notice on the right, as I'm drawing my visualization, the system is trying to infer my intent with regards to the structure of the visualization. We designed Data Garden to support a specific subclass of visualizations, namely hierarchical visualizations, in order to be able to do this semi-automated recognition. Namely, in this visualization, there are 3 hierarchical levels. First, the parent branch, then the sub-branches, and finally the leaves, which are children of the sub-branches. Once we've drawn the visualization, we then need to switch to specifying the data mapping. For this, we have the Dimensions tab. This tab enables us to add dimensions and specify how they are converted to strokes. I start here by choosing the middle level of my hierarchy, the sub-branches, and binding each to a different day value. I can then also specify what this dimension represents. I then switch to binding my color dimension. As soon as I choose color, the system is able to determine that I have 2 different colors and can therefore infer that I intend to have 2 categories and sort my strokes accordingly. Data Garden also supports continuous visual channels and dimensions. Here, I choose the position channel. The system displays its interpretation of the stroke's positions, and I can specify my data range. The system can infer based on the positions of the strokes and what values represented, or what values entered here, what value is being represented by each stroke. Once I have finished defining my mappings, I can switch over to the table. Oops, sorry. The table represents what data is currently being represented by the system. In other words, what has been inferred from the visualization. There we go. Okay. So Data Garden demonstrates a system that supports a sketch-based templating workflow, and there were a number of technical and interaction challenges that we needed to address in the implementation. First, we needed to support the ability to structure sketches, since it is this structure that conceptually links our visualizations and our data. To keep the sketch-like flow, we implemented some simply heuristics to infer the structural intent. In this example, or in the example given in the video, the system was easily able to infer the correct intended hierarchy. However, as glyphs and hierarchies become more complex, those relationships might become more difficult to infer. Here, there's ambiguity in which strokes are meant to be a single glyph, but I can specify it manually in the overview. I can also correct the parenting by specifying that the gnome is meant to be a child of the grassy track. To support machine-assisted data mapping, we need good mechanisms to support us in understanding what the machine is understanding and interpreting. For example, we use colored highlighting and a mini representation of each gnome to help me understand what the gnome's position mapping is. We also need good mechanisms not only to make corrections, but also to specify values. Here, I meant there to be 3 different shapes and 3 different values, so I can specify that and directly manipulate the icons to indicate which gnome belongs to which. Finally, to make this workflow complete, we need to be able to use the template as a template to apply data and generate the visualization. It wasn't our goal when implementing Data Garden to create a robust solution to the generation problem, but we did want to demonstrate how the templates could be used, so we implemented a naive algorithm for doing the generation. To explain a little bit about how this algorithm works, when you take your template and enter a new data set, the system reviews the rows to see which values have been updated and will update the position, angle, color, etc. of the existing glyphs. It will then look at new rows and add additional glyphs by copying glyphs from the template and updating their position, angle, etc. It works surprisingly well, both in relatively simple as well as in more complex templates. It definitely does have some limitations, which we will talk about in a minute, however. So in order to evaluate Data Garden and the sketch-based templating workflow, we conducted a reproduction study, a freeform study, and created a gallery of visualizations. In the reproduction study, we asked 12 participants to produce a visualization based on the reference on the left, which we modified from the Dear Data project. Participants were not required to reproduce the visualization exactly, and we observed that the sketching workflow really supported them in adding their own personal flair to the visualization tasks, such as for P1 and P4. Some participants really understood the templating concept, including only just enough glyphs to specify their visualization, like P9, whereas others preferred to reproduce the inspiration more exactly, like P10. In the freeform study, participants were asked to create a visualization for a dataset of their choice. We also asked them to try out the template with a small dataset, which we provided. Generally, participants really liked the workflow. E1 described it as the more fun way to specify a visualization. The workflow also helped participants think through and formalize their data structures. They mentioned points such as having to think through possible data values, consider extreme values, etc. However, you might notice some visual problems in the visualizations generated from these templates. Data Garden is mainly designed to support specifying explicit data mappings. This is necessary, and we know it's necessary because the only way for the system to know what the visuals represent is for us to say so. But when I draw the visualization, there's a whole bunch of implicit constraints that I don't mention. I don't need to tell you that the sub-branches need to alternate sides of the main branch, or when I add extra branches, you should make the main branch bigger to make space, or that leaves should not overlap. In this research, we aim to demonstrate the potential of the sketch-based workflow, and I would argue that not only have we shown what you could do with it, we've also demonstrated the challenges that still lie in the way of doing it well. How can we automatically recognize these implicit aesthetic intents? And given that automated systems will at some point fall short, how do we design tools to support the explicit specification and correction? Do we need fancy recognition and generation algorithms, or can something simple like the heuristic we implemented plus a good correction interaction do the trick? These are great avenues for future research in this area. I'd like to take a quick moment to thank my colleagues who made this work possible. The application, as well as the visualizations from the gallery, are all available online. If you're interested in this work or in using the Data Garden code, please get in touch. And yep, that's me.
Thank you very much, Anna. Let's have a look to see if there are any questions. I can't see any new questions in Slido, but I've sort of got a question. One of the aspects I think you might have written this in your paper is sort of this idea of legends, and that people are making perhaps their own mappings, and that are not that someone else coming online might not understand or whatever. Could you tell us a bit more about the issue and then maybe some solutions around it?
Yes, so there's kind of two different issues that we're dealing with here. One is how people want to specify these legends. So the way the system is set up with the templates, it would actually be very easy to automatically generate legends for the visualizations. But we saw is that creating the legend was something that participants sometimes wanted to do with the visualization. That, of course, makes the recognition process that much more complicated, because then you have two completely different entities that you need to be able to parse. So yes, there's kind of two different ways to approach this. If we want to do the simple solution, dead easy, like just takes a day of programming. If you want to do the recognition side, that's where things get complicated.
And in a way, could you sort of tell me a bit more about the sort of mappings of the value? Because in a way, you don't really have a notion of size to value or things like that. It's more about position. Is that right?
So there were, I think, 6 different channels that we implemented. We included angle, position, as well as size as the continuous values. So we can do mapping from size to glyph. It does get kind of interesting, though, with these kind of idiosyncratic hand-drawn glyphs. We included 2 different size metrics. One is the length of the glyph, which is based upon the glyph side or spine. I didn't really have a chance to get into that in the presentation, but there's actually a more complex structuring system underneath the glyphs where authors can specify what the kind of linear structure of the glyph is meant to be. So we can use either that or just the straight up, bounding box area of the glyph to determine things like size.
Okay, brilliant. Well, thanks so much. Thank you, Anna. And there's a bit of conversation going on in Discord, so I think it'd be a good place to continue some of this. I'd like to thank all my speakers in this session for keeping to time and presenting some very interesting work, and thank you also for the technicians helping me out to play those videos, and the student volunteers for all their help in that session. So I think now we have a break, but also heads up, if you're interested in what's happening next year, there's the VIS 2025. Are we really 2025? Amazing. 2025 kickoff that you might like to check out. So thanks very much for my speakers again, and see you in the next session. Thank you. Bye.